Alright guys, this video is going to pick up with the section 6.3 material. So these are going to be our function operations and our function composition work. In problem 4, we have two different functions. We have f of x, which is equal to 3 times x to the negative first power, and then we have g of x, which is x minus 8. So first up it says, what's the domain of g of x? Well, g of x is just a linear function. And any kind of polynomial is going to have a domain from negative infinity to positive infinity because you can plug any x value into those equations. So for g of x, remember that you have a couple of options for writing that. We can say all real numbers, or we can use inequality notation and say that our x values will fall between negative infinity and positive infinity, or we can use interval notation and say that exact same thing. So that's g of x. I can plug anything in there. F of x is 3x to the negative first, which is really the same thing as saying 3 over x. So this is a specific kind of function we'll talk more about in our next chapter, chapter 8. But my issue here is that this particular function has one x value I can't plug in. And that x value is 0 because I can't divide by 0. So if I want to write this domain out, I'm just going to write it as x cannot equal 0. So it can be any number, it can be positive 1,000, negative 100 million, it doesn't matter what, it just can't be 0. So then we're going to get started with the function operations. We can be asked what is f of 3 plus g of 3, or this same notation could be used as well, f plus g of 3. Those are equivalent operations. So if I want to find this out, f of 3 plus g of 3, I'm just going to plug 3 into both of those operations. So when I plug that into f of x, I'm going to use this 3 over x setup instead of the negative first power. So I'll have 3 over 3, and then g of 3, I'm going to plug 3 in and get 3 minus 8. So this will simplify to become 1 plus negative 5, which is equal to negative 4 as our final answer there. This problem continues on to the next page. So now it asks us to find what is g of x minus f of x, which is the same thing as saying g minus f of x. So I can either write the notation as two separate functions, or I can write the operation that's going to happen between the functions and then what variable its operation involves. So here, g of x minus f of x, my g of x was that x minus 8. And then my f of x is that 3 over x. Not a whole lot else I can do with this operation. There are no like terms, so it's not going to simplify anymore. So x minus 8 minus 3 over x. Then we've got some function composition work. So D says, what is f of g of x? So g of x is x minus 8. So this is the same thing as plugging x minus 8 in for x in the function f. So f is this guy, the 3 over x. So I'm going to take x and fully replace it with x minus 8 down here. So this is going to be 3 over x minus 8. And that's our composition function. Then we're going to do the reverse. We're going to do g of f of x, which means we're going to evaluate the function g at the function f, which is 3 over x. So I'm going to take 3 over x, I'm going to scroll up once more, and I'm going to fully replace this x here with that new function of 3 over x. So that's going to be 3 over x minus 8. So it's useful to note that these are not equivalent operations. They're not the same. 3 over x minus 8 is different than 3 divided by x, that quantity, and then subtracting 8. Part F says, what is f of g of 9? So there are two ways I could go about solving for that. One thing that I could do is just find my f of g of x and plug 9 into that resultant operation. So what that means is I can just take this final result, plug 9 in, and I've got 3 over 9 minus 8, which is the same thing as 3 over 1, which is the same thing as 3. So that's one option I could use. The other would be to find g of 9 first, which would be 9 minus 8, which is 1, and then to find f of 1, which would be 3 over 1, which would be 3. Either way, you get to the same final answer. But if you don't have to solve for the f of g of x first, sometimes it's easier to do that numerical replacement instead. Number 5 is also some more function operations and some function composition. So we have f of x equals 27x to the 1/4 power, and then we have g of x equals 16x to the 1/3 power. And first up, just like before, we are asked, what are the domains of these functions? So for f of x, that is an even-valued root. Even-valued roots require that we plug in 0 or above if we just have an x in the root. And that's because we can't take those roots with negatives unless we end up with imaginary numbers. G of x, though, is an odd root, which means we can plug anything in. So we can go from negative infinity to positive infinity. Any number is good to go. Part B asks us to do some function multiplication. So we're just going to take f and multiply it by g, which means I'm going to take 27, x to the 1/4, and multiply it by 16, x to the 1/3. That's going to be kind of a big number. If I multiply 27 by 16, I'm going to get 433. But then what I need to watch out for is I'm multiplying x to the 1/4 and x to the 1/3. So those exponents are going to have to add. But right now they do not have a common denominator. So I can make 1/4 3 over 12. I can make 1/3 4 over 12. And when I add those together, they are going to be 7 over 12. So this will be 433 times x to the 7/12 power. And that's my multiplication operation. Then I have a function composition in part C. It asks me, what is f of g of x? So that is the same thing as saying f of 16x to the 1/3, which is the same thing as fully replacing the x in the f function with 16x to the 1/3. And I'm going to raise that to the 1/4 power. So let's see how this simplifies. The 1/4 needs to go to 16, and it needs to go to the 1/3. So I'm going to have 27 times 16 to the 1/4 power times x. When I multiply 1/3 and 1/4, I'll get 1/12 as my exponent here. And then I just want to check and see if anything's going to simplify a little bit. 27 here, 16 to the 1/4, that's the same thing as the 4th root of 16. Can't really do anything with the x to the 1/12 though. The 4th root of 16 is a nice and easy number. It's going to give me 2, and then still x to the 1/12. 27 times 2 is going to become 54 x to the 1/12 power. And I can go ahead and box that up right there. Very last one, g of f of 1. This is one of those examples where I don't have to find g of f of x first, so sometimes the numerical operation will go by faster. So if I solve for f of 1 to begin, f of 1 gives me 27 times 1 to the 1/4. 1 to any exponent is just 1, so this is going to be 27. And then I can find g of 27, which is going to be 16 times 27 to the 1/3. A 1/3 exponent is the same thing as a cubic root, so cubic root of 27, which is going to give me 16 times 3, which is going to give me 48 as my final answer here. That's it for our function operations and composition in this particular review guide. Next up, we've got some inverse functions to work with. So first, we want to find the inverse function of a line. This line is y equals 3x plus 11, or f of x equals 3x plus 11. So in order to get started finding our inverse, we're going to swap our variables. So we'll have x equals 3y plus 11. Then I'm going to solve to get y by itself. So I'll do x minus 11 equals 3y. Divide both sides by 3. And I'm just going to rewrite this out. So I'm going to say y is equal to x over 3 minus 11 over 3. Now here, this problem asks me to confirm my result. So in order to do that, the operation that I can perform is to find the composition of a function at its inverse, which means I just need to take the inverse function and plug it in for x in the original function. So I'm going to take 3, and then instead of writing x, I'm going to write this whole operation, x over 3 minus 11 over 3 plus 11. So if I were to distribute this in, this will become 3x over 3 minus 33 over 3 plus 11. And this is going to simplify to x minus 11 plus 11. My 11s will cancel, and I'm just going to be left with x. And that is what we need to have happen if we've correctly found our inverse. That either taking the function composed at the inverse, or vice versa, the inverse composed of the original function, we will just get out a single x completely by itself. Let's try this one more time, but now we're going to do a power function. We're going to do 2x to the 7th minus 1 instead of a linear function. So here, this 2x to the 7th, I'm going to call this y instead of f of x. 2x to the 7th minus 1. I'm going to swap my variables, so x equals 2y to the 7th minus 1. I'll add the 1 over, so I'll have x plus 1 is equal to 2y to the 7th. I'll divide both sides by 2. And then I'm just running out of room a little bit here, so I'll come right on over here. Y to the 7th is equal to x plus 1 over 2. And then I need to take the 7th root of both sides. So y will be equal to the 7th root of x plus 1 all divided by 2. So that's my inverse function here. Now again, we want to make sure that we can check the composition operation to confirm that it is the correct value. So if I take the function, compose it at its inverse, or take the composition at its inverse, what that means is this x in my original function is being fully replaced by this entire 7th root operation. So here's what that will look like. I'll have 2 times, got this big 7th root of x plus 1 over 2, but then the x in my original function is raised to the 7th power. It's my dog growling. To the 7th. And so what will happen here, you guys, is that the 7 here and the 7 here will cancel. Stella wants to do math in the background. I don't know if you can hear her, but I don't think she likes that I'm talking to the video. So my 2's are going to cancel here, and I'll have x plus 1 minus 1, and that's going to give me x, which checks out here, and I'm going to go get my dog a treat here, guys.